All right, guys, let's get started on this last chapter of the year that we're going to go through. Chapter 19, Climate Change and Ozone Depletion. So we'll start with Section 1 here. Section 1 will break into a couple for you. It's pretty big. So let's get to the nitty-gritty of things. So global warming and global cooling, not a new thing by any stretch of imagination. So the Earth's roughly 4.7 billion years old. And in that amount of time, the climate has been altered or has altered itself, or however you want to say that, many, many times. Volcanic emissions alter the climate of the planet. Changes in solar input, how much the sun is kicking off. Movement of the continents and impacts of meteors have altered our landscape and our climate throughout history. And so this is a series of graphs that show kind of some of those changes that have happened. So over the past 900,000 years, the troposphere has changed from global warming to global cooling, and that's what this picture on top here is really showing you. So this is the surface temperature of the Earth over that period of time, the last 900,000 years, and you see that there are spikes and dips, and that is a very naturally occurring thing. And it is very common for those cooling and warming periods to exist. The book ascertains, and most global scientists, which we'll talk about here shortly, global atmospheric scientists, really have focused on this bottom graph, though. These are the changes that have occurred in the past 22,000 years, and so much more recent time. And so if you go back to 22,000 years ago, that was the end of our last ice age. And so you can see the temperature changes from that period of time. Make note over here on the left, these are important numbers. -5 is the bottom of this graph, which means the only difference between an ice age and what we're currently existing in is a difference of about 5 degrees globally. So when you think of global warming or global cooling, that natural process, we're not talking about huge changes in temperature. We're talking about a matter of less than 10 degrees of movement that is creating significant changes on the planet. And so you can see that that global warming had occurred and got us out of the last ice age. And so at the end of that, then basically here's where agriculture was established. And then the average temperature for the last 10,000 years has been pretty much about 15 degrees Celsius on average. And you see that this showing you it wafts back and forth, but never more than a degree at any point in time. So there's been very little movement for the last 10,000 years about the temperature. It's been very stable. Now if we break that down a little bit further and we look for the past 1,000 years at the temperature, we've remained fairly stable. But we've slowly begun to rise a little bit. And so over the past 1,000 years, you'll see that graph's down here at the bottom, and you see it's kind of back and forth, back and forth, back and forth. And then here in the very end of it, we have seen a marked increase in temperature over that last little ping. So that increase right there happens to coincide with basically the Industrial Revolution. Industrial Revolution, large-scale deforestation, and wide use of fossil fuels correlates with this huge change in temperature right here at the end. And so, does it cause that? That's debatable, of course, but it does coincide time-wise with those pieces. Up here on the top, it breaks it down in a little more detail, these spikes with you, to show you what happened from basically 1880, the start of that process, to now. And you'll see that it's been back and forth and up and down, but there has been a slow progression upward in the process. With that, they've also done a series of research and collected data. And so actually on Mauna Loa volcano in Hawaii, they've been collecting CO2 levels since 1958. And so this is the breakdown of those CO2 levels. And you see that they have dips and spikes, dips and spikes, dips and spikes. The CO2 level measurement around the globe alters based on seasons a little bit. But you can see that there is a steady curve or increase in CO2 level that's been gathered since 1958. And this is commonly known as the Keeling curve. And it's named after the dude who supervised the measurements, basically. Keeling curve is an indication of the CO2 levels again. And so moving on here, just looking at a couple more graphs for you so we have a complete understanding of what's going on. So estimating the global change in temperature, you see that there's a series of pictures here showing you different correlations. So this is atmospheric carbon dioxide, and this is looking at ice cores. And ice cores are a really important piece of understanding global warming, which we'll talk about in here in a little bit due course. But if you look at the CO2 levels, starting 1000 AD and moving your way forward, you see that the CO2 levels have spiked significantly. If you look at this picture here, this has to do with temperature changes, and you see that, boom, there's a huge spike in that in the last little bit of time. And the temperature anomaly, or the hockey stick analogy, where it stays fairly steady all the way through here, and then all of a sudden we have this end, and it looks like a hockey stick. Okay. So that has to do with the IPCC, which we'll talk about in due course here as well. But you see all of these data points are showing changes in very recent time, huge upward swings. If you look closer and you look at temperature and you look at CO2, there's a pretty close correlation between those two things. And so blue is the temperature variation throughout 400,000 years of data that we can trust pretty well. And then red is CO2 level. So blue is temperature and red is CO2 level. And you see that those things are pretty much hand in hand. When one spikes, the other one spikes. When one dips, the other one dips. And there's a pretty good correlation between CO2 and temperature. And we know that. We knew that throughout history. This picture down here below is actually from An Inconvenient Truth, old Al Gore's movie, showing you that correlation between the two. This is the more accurate picture up here. That's a simplified version down there. So this is the more accurate version with a little more detail in there. Scientists have historically believed that CO2 level was a result of temperature. So when you change the temperature, it changes the amount of CO2 in the atmosphere. So CO2 is the result of temperature change. We are now in a situation where we've added significantly more CO2 into the system. And the question is, what is the temperature going to do as a result of that? Again, historically, we believe that the correlation was the other way around. Temperature results in CO2 change. So that when we add CO2 in, what does that do to the temperature? And that's the question mark. That's what scientists are attempting to figure out and understand and answer. And that's where the debate lies, if you believe there to be a debate. And so, how do we estimate all these temperatures and things throughout history? Well, we've used a variety of sources to understand and analyze this kind of climate of the past. We've taken direct measurements in detail since 1861. So we have those. We use tree rings. Tree rings are good indications of lots of things for us. We can look at pollen in deep lakes and bogs that give us indications about temperature and things. Bat dung deposited in caves for thousands of years. Ocean floor sediments, radioactive isotopes in rocks and fossils, past glacial formations, and then here's the biggest one, the one that we really use the most of. That is, we look at air bubbles inside of ancient glaciers, little air pockets that were frozen in there forever ago. Basically give us a little encapsulation of the atmosphere at that time. And so the way they get those out is they dig ice cores. Ice cores, you can see these guys down here have this big, long, twisty tube. That's the core, that's the drilling bit itself, and then inside of it, these things down here are the actual cores of ice. So this is actually a cross-section. The core is this whole length, and it's been sliced down sideways, and that's what they're holding up to show you in this picture here. So ice cores are used for all kinds of things. We can figure out what the composition of the troposphere was at the time, different gases and things. We can look at temperature trends within that time period because different gas levels and ionizations and all those kind of things give us an indication of the temperature at the time. We know the greenhouse gas concentrations at the time. We know solar activity. Based on this, we can know snowfall amounts and forest fire activity. All of these pieces of data can be collected from these ice cores. And so they're really handy pieces of information for us to understand. And so we get really accurate data by looking at these ice cores. And so what causes these temperature changes on the planet that we're paying attention to and looking at with ice cores? Well, there are basically three major factors that we look at when we look at Earth's climate. How's the sun is the main one. And so when the sun changes, it alters our climate. The oceans, for a couple of reasons, they store both CO2 and heat, and they are part of the water cycle. And so as a result, they have an impact on it. And then the greenhouse effect, of course, which is a warming effect in the lower troposphere of the atmosphere and on the surface, and it is affected by greenhouse gases. So this picture right here shows you this. And the greenhouse effect is a naturally occurring process, and it's an important process. We need it. Sun comes in. It comes in as light, gets absorbed into the materials on the planet. Those materials on the planet then convert and re-release that as heat, so it's in a different form. Now, some of that sunlight hits clouds and bounces off, or hits the surface like snow and stuff like that, and bounces off and goes back into space, and it never results in heat at all. But the stuff that gets absorbed in the Earth's surface then gets re-radiated as heat, and it radiates all the way back out into space if it gets a chance. What we have is greenhouse gases, gases that are in our atmosphere, that when that stuff tries to re-radiate back out, it gets absorbed into those gas molecules and then radiated in a variety of directions, resulting in more and more heat being held down in the lower atmosphere, making it hotter and hotter. So that's what the greenhouse effect is, and it is a natural occurring process. The average temperature on the planet, by the way, is about 57 degrees, so we look at that. If we didn't have this natural greenhouse effect with these things in our atmosphere, the average temperature on our planet would be about a -2. And that's not very sustainable for life on the planet. So the greenhouse effect is absolutely necessary in moderating of the temperature for us and maintaining a temperature. And that greenhouse effect is a result of several different elements or gases that exist. The first one is water vapor. The amount of water vapor causes more heating, or holds more heat, which results in more water vapor being created. And as a result, more water vapor makes more heat makes more water vapor, so we get a positive feedback loop from water vapor in the atmosphere, and that varies a lot around the globe depending on if you're in a wet or dry area. CO2 is another one. CO2 is the most common one that we discuss. CO2 is part of the carbon cycle. It's sequestered in lots of plants and animals. And so we burn it with fossil fuels, and so CO2 is kind of a big one that we look at. It's quite abundant and has a big impact on things. Methane gas is another one. It exists in fossil fuels, it exists in decaying organic material, and it occurs in livestock, for instance, produce a lot of methane gas. And then nitrous oxide is the last one. It's usually emitted from agriculture and industrial practices and fossil fuel burning as well. But here are 4 major greenhouse gases that have a huge impact on things. This graph is a breakdown of those different gases, and there are correlations with temperature as well. So the first one's CO2. The second one is methane. This is actually the temperature throughout the last 400,000 years. And this one down here, if I remember correctly, oh yeah, this is sea level. And so you see this correlation between CO2 level and methane level and how those change, and you see they're very similar spikes in similar locations. Here's temperature, which is more directly correlated to CO2 than it is methane, if you can tell. But they're all closely linked. There's peaks at the same time in all of them. And then how that has affected the sea level on the planet, and you see those peaks correlate as well. So all of these things tie together with each other. Temperature changes will affect sea level, and methane and CO2 affect those things as well. And so there's a big correlation between all of them. We'll continue on in just a little bit.